a very bad experience last year during the last semester. So we learned out of that.
That's good.
So I think that we still can wait a few more minutes. We wait to start at 30 sharp. So you agreed to be registered, to be recorded, right?
That's fine. Yes. Yes.
Thank you. Because I had a number of emails today from friends and colleagues saying that they could not make it, unfortunately, because it's in the middle of the teaching semester.
Yes.
In fact, even Paolo De Bernardis was not able to attend because of that's another commitment that exactly at the same time. So he was very sorry for that. So it's good if we can record the talk.
That should be fine.
And then depending on your commitments, Joe, if you have some more time to spend with the students after the talk, if it's fine for you, it would be nice for them to talk to you, ask some advice or on their projects, if you have time, of course.
Yeah, that'll be fine. We can spend half an hour or whatever they like. So, yeah.
Yes, more than that.
Yeah, sure. Yeah.
Okay. So let me say again to the attendants that if they want to ask questions, they can write on the chat, and eventually at the end of the talk we will try to address all of these and additional ones. So if we all agree, I would like to start by really thanking a lot Joe for being so kind to agree to give his lecture remotely, and it's of course a great pleasure, an honor for us to introduce him as the fourth Quid Ultra colloquium speaker. Joe, as we learned in the past few weeks, it was hard to catch the right email to write him because he has 3 different affiliations. And he's currently Homewood Professor of Physics and Astronomy at the Johns Hopkins University in Baltimore, an emeritus researcher at the Institut d'Astrophysique de Paris, and a senior fellow at the Beecroft Institute of Particles Physics and Cosmology at the University of Oxford, although he's now connected from Paris. Joe obtained his PhD in astronomy at Harvard, and after a few years, he took his first position at Berkeley. And after nearly 30 years, he returned to the UK to take up the civilian chair of astronomy at the University of Oxford. And during his really amazing research career, Joe has published more than 900 publications, most of which related to cosmology, particle astrophysics, and galaxy formation. And he has done fundamental work on the cosmic microwave background. His pioneering predictions of the damping of cosmic microwave background radiation fluctuations have been verified by several recent experiments. He has greatly contributed to the exploration of the nature of dark matter and to the theory of galaxy formation and black hole evolution. And 3 of his publications have been cited more than 1,500 times. One is a review article on evidence, candidates, and constraints on dark matter that he wrote in 2005 with Gianfranco Bertone and Dan Hopper. One is the very famous paper with Martin Rees in 1998 on quasars and galaxy formation, where they first derived a relation between the mass of the central supermassive black hole and that of the galaxy's spheroidal component. And the third one was on the origin of dwarf metal-poor galaxies with Avishai Dekel in 1986. So he received an International Balzan Prize for his work, and he has published several popular books. He's a member of the National Academy of Sciences and a fellow of the Royal Society and of the American Academy of Arts and Sciences. He most recently received the Gruber Prize for Cosmology in 2019. And so we are really pleased to invite him to present his personal view of the future of cosmology. So please, Joe, I leave the floor to you.
Raffaella, thank you so much for those kind words, and greetings, everybody. I'm sure there are many friends out there that I can't see, but you can see me at least. Rome is one of my favorite places. It's a real shame that we have to do this in such an impersonal way, but hopefully that would change in the next year or so. So let me begin. I'm going to give you a very broad brush view about where I think cosmology is going, what the future is for the field. And here is the bottom line of what I'm going to tell you about. It's the moon, basically. So I'm going to argue that we will have new telescopes on the moon. And it's by far the best place to build large telescopes. Why? Well, you have this stable platform. You can imagine, going into space, putting telescopes there, which we're doing, obviously. But if you want to do something big, then the budget is huge in space for a free flyer. But on the moon, we're going there anyway. We're projecting to do many things on the moon. And building a few telescopes will be such a tiny part of the overall cost, compared to, think of the Hubble Space Telescope was a tiny fraction of the cost of the Space Shuttle and the National Space Station. That's probably why it got funded. Without that huge, space effort, we probably wouldn't have our telescopes in space to the same extent we do now. Anyway, the moon is going to be something like this. My argument will be partly for radio astronomy at low frequencies. It's such a unique place to do that, especially on the far side of the moon. It's an amazing place to do far infrared astronomy too. I'll argue for that, and optical astronomy, and even gravitational wave astronomy. So all of these things I will touch on, not in enormous detail, but to try to give you a flavor for what we can be doing on the moon. And above all, it'll be cosmology, I think, as the overall case that I want to make as where we will be there to make real progress. So let's go then to cosmology. So we have this remarkable pioneer of physical cosmology, Georges Lemaitre. All of you know this well, but this is from his sketchbook in 1927, where you can see that he has a family of models of the Big Bang, in which expansion first decelerates, and the modern view is this is due to dark matter. And then at late times in many of these models, it accelerates. And again, the modern view, it is due to the effects of dark energy and the cosmological constant. But what is quite amazing is that in 1933, Lemaitre was fully aware of what dark energy was. He talked about the equation of state, P equals minus rho c squared. You see it there. And he was aware, this was the beginning of the quantum theory decades, basically. He was aware of quantum fluctuations, giving you negative pressure, negative energy density, and therefore effectively leading to an acceleration. And so he saw all of this. And you can ask the question, okay, that was an awfully long time ago. We've now had, about 80 years progress. How much further have we really gotten? And so maybe the biggest breakthrough in cosmology came about with the theory of inflation in 1981, where you could see it has really led us to quite an astonishing picture in which you begin from essentially nothing or almost nothing, And thanks to an early period of dramatic acceleration, you get to the universe that we see now, and leading to structure formation from density fluctuations generated in that early phase of inflation from boosted quantum fluctuations. That's our current theory. However, this is a wonderful theory, but we really would like to verify it, to have some proof that some predictions. And so we're on a very long journey now to try to test inflation, look at its predictions. So I've indicated here some 5 expectations of inflation. Well, I mentioned dark matter. That's responsible for the early deceleration of the universe. We haven't found it. And there's no immediate prospect, I would say, even though we believe it's most likely some weakly interacting particle, hard to detect. In principle, we've made experiments that can look for it. We have no immediate detection on the horizon. It's hard to predict when we'll find it. I'm confident we will someday, but it's not clear. Likewise, dark energy, which is equivalent to Einstein's cosmological constant. It's wonderful. It's a constant, explains the acceleration that we've measured in the past 2 decades because it's a small constant that comes into force only at very late epochs, and so then begins to accelerate. But we have no understanding of this, and we haven't seen any variations in it, which might lead to some new physical insights. So I've given those sort of, for the moment, red marks. Then there are, because I don't see any immediate guarantee of any science return in progress in these areas. Well, let's move on. Then there's the gravity wave background. So this is a wonderful prediction of inflation models. It predicts there should be a tensor component to the microwave background fluctuations induced by early gravity waves generated at the end of inflation. And so we're desperately looking for these. It also predicts that galaxy formation in our standard model of cold dark matter forms from small clouds which build up into bigger and bigger ones. Now, the biggest clouds we see as galaxies. We can monitor their history from studying them. But the small clouds, which are left over as dwarf galaxies, but far more with the building blocks to the big galaxies, and the theory predicts there should be a lot of them around, but we have no proof of that. Now, there is a prediction that as these small clouds in the very early universe are coupled to the radiation, there should be a friction between the radiation and the small clouds. The small clouds, the fluctuations end up surviving as cold dark matter, of course, but the baryons in them have dissipated, and that should leave a signal in the microwave background, a spectral distortion, a slight deviation from the black body spectrum. That's a prediction. And then the final prediction is that normally much of what we do in general in astrophysics consists of looking for distributions that are essentially Gaussian. Again, the central limit theorem always takes you in that direction when you develop any theoretical understanding of the parameters of the universe, of where they may come from. But inflation does generically predict a non-Gaussianity in the initial conditions. So that's another thing that we could look for. You'd expect to see this most easily in the temperature fluctuations, microwave background, as slight twists from Gaussianity. So those are basically the areas that we will be going into. And what I'd like to now argue for you is that it's going to be a very, very challenging, and I'm going to make a case for lunar telescopes as being our best solution. So let me begin just by summarizing the dark matter story. So here we have this incredibly large parameter space where dark matter particles, which are inferred to be weakly interacting, they're not shining particularly. We see them in the dark, as it were. There's a wide range of possible particle masses and a wide range of possible particle cross sections in principle that are possible. And at the bottom, you have purely gravitational interactions. And so all of these are possible, and we need some guidance. And so it turns out that we're motivated by in two different ways. One is to look for theories which are plausible, which are attractive for one reason or another. And I've highlighted three areas where there is, some theoretical motivation. But then you also, because there's so much parameter space, you need some motivation to look in these areas. One has come from the so-called anomalies in dwarf galaxies, the fact that they have properties that don't easily fit into the standard model of cold dark matter. The difficulty here is that, we have standard and complicated astrophysical processes to do with star formation and massive black holes heating up the baryons and doing all sorts of complicated baryonic physics, that there's no guarantee that we need to go to particle physics to explain these things. So the one increasingly popular target for dark matter is the pure gravity option, because here the physics is not exotic physics, I would say, in terms of just model building some new particle. It's based on objects that we know exist, black holes. It's based on general relativity, which predicts them, and on the inflation theory and its variants, which allow you initial fluctuations, which can be large enough to make black holes very early. And the beauty of this hypothesis, if it were true, is that you need to make very, very few very early when the universe is highly radiation dominated, because at late times they will be, they could be all the dark matter. The problem with this has been the following. We've had a big breakthrough in looking for black holes. In fact, the early suggestions from the Greenwich wave experiments, we might even be seeing some primordial black holes. But the current view is, when you look at the events that we see and the attempts to explain those events, these are solar mass to 100 solar mass merging events. If there are primordial black holes masquerading for some of these sources, and some people are convinced there are, but we're fairly sure that if that is true, they're at most 1% of the dark matter. And even though you can see on the right that you have enormous freedom in the initial conditions to make these black holes, and we have good theories of how they're made, they're 1% of dark matter, so they won't tell us what the dark matter is. Okay, so that's a missing ingredient for the inflation theory, our preferred theory of cosmology. Where do we go from there? Well, dark energy has made a lot of progress since the early days. But I show you here the progress in the equation of state in W, this parameter that Lemaitre really introduced in 1933. P equals minus W rho C squared. W is -1. Bingo, you have a constant. The error bars were huge in 2001, but there was still enough to guarantee eventually the Nobel Prize for discovery. But when it comes to the most recent data, the error bars have greatly shrunk, but you can see they're centered on the cosmological constant, the -1 value. And this is with a combination of increasingly precise modern measurements from supernovae and microwave background and density surveys of galaxies, the baryonic acoustic oscillations, etc. And it's hard to see as we move forward in time where there might be, or when we might expect to find a deviation from -1, which would at least be a hint of new physics. And so if we keep on measuring this same -1 Einstein's cosmological constant value, then that's wonderful. It means we're approaching some standard model, but are we learning anything new? Because we had this suggestion many, many years ago. So in terms of testing our understanding of fundamental cosmology, we may want to do something else. So that something else is, of course, the microwave background. We've made this wonderful progress with the Planck satellite following many other experiments. we have this beautiful model of temperature fluctuations in the sky. These reflect the initial fluctuations through which all structure formed. And we've now got a precision of a few microkelvin. We have to do much better to see if we can get to the gravity wave fluctuation imprint that many inflation models predict. This involves going from microkelvin to nanokelvin, a huge improvement. But we've done that in the past. And we have experiments now under design to take us a major part of this way, both in space and eventually at the South Pole in maybe 6 or 7 years' time. And so that's the time scale, and the goal will be to look for this elusive B-mode signal, a gravitational wave shearing signal in the microwave background, which should come in at very low multiple numbers on large angular scales when it was imprinted early on. The problem is with this very challenging goal is that the predictions are uncertain because we don't exactly now know how inflation ended, when it ended, and the tensor to scalar ratio, this gravity wave prediction, this red question mark, is uncertain by many orders of magnitude. So to summarize, there's no guarantee of a signal. It's a wonderful thing. We are pursuing it. We must pursue this, but we would ideally like an experiment with a guaranteed return to advance really fundamentally in cosmology. So this now brings me to what we're going to be doing in space. And so I would say that there's one area of astronomy and cosmology that's really very, very poorly understood. We're just beginning to probe it, and terribly naively so far, but that's because it's so difficult. This is the dark ages. So to summarize, when you look at the microwave background, you have basically a few million pixels on the sky, and then the damping of the fluctuations kills off the power. And so this summarizes the information content you have in the universe, basically a few million bits of information. If you go to large scale galaxy surveys, your horizon opens up. Suddenly we have future surveys with Rubin, etc., which will have billions, maybe 10 billion redshifts. So it's hard to go from that to the number of independent bits of information because every galaxy is somewhat different. But a rough guess is that you might expect 100 million modes of information from large-scale structure surveys. And that's indicated schematically by this green line as we move through to smaller and smaller scales. And so that's a huge increase. That's 100 times more information content than from the CMB. That may not be enough. I'll show you in a moment. There is one ultimate place that we have to go to, that we will go to, where there is incredible information, and that is the dark ages. Why? Because each galaxy is made of millions of cloud-like building blocks. And these leave a 21 centimeter signal in the universe long before the stars formed, in the dark ages. And we see them basically in absorption, because it's cold gas, fluctuations really, against the microwave background. And so this way, if you could get a million building blocks per galaxy, then roughly speaking, you can see we suddenly now are talking about trillions of modes. And that's what's possible in principle in the dark ages. And that would be enough with this information to do the most amazing cosmology you could ever dream of doing. So that is the goal. And let me try to tell you how we might get to that point. So this is what we want to do ideally. So starting, in the recent past, we already are probing reionization by studying, quasars at redshift 6, 7, 8, etc. And we know the sources of radiation that ionize the universe come both ultraviolet photons from stars and also from AGN, X-rays from AGN. And then as you go back further in time, before when the first stars were forming, you had Lyman alpha production. And throughout all this epoch, the gas temperature, the spin temperature, which is what you're looking for really as an absorption signal, is coupled and messed up by astrophysical sources, coupled to the gas temperature. But once you get to the dark ages where there were no stars, then the gas is colder than the microwave background radiation, the fossil radiation. It's on a different adiabat, it cools down. So in principle, in the dark ages, you can see an absorption signal, and here it is in the bottom panel. As I go back in time, then the sweet spot is roughly redshift 50 or so, but I can see absorption, the shadow of the clouds against the microwave background. And this would be long before there were stars. This would be measuring the primordial fluctuations in the gas density. And because there are so many modes in principle, one could open up enormous information content and do cosmology with an accuracy one could not do in any other way. So that is basically the idea. Okay, and what I'm going to argue is that there's only one place we're going to successfully do this, and that's partly because I want to go to redshift 50, and that is the moon, because we are looking at 21 centimeters, and that is such a low frequency that the Earth is not a good place, not the best place to do this. Okay, so 30 megahertz astronomy. Why the moon? Well, you want to go to the far side of the moon because that is the most radio quiet environment in the entire inner solar system. You don't see the Earth at all. We don't get, marine radar or cell phones or TV. And what is more, there is no ionosphere on the moon. And that is the real problem, actually, when you want to look at 30 megahertz. It gives you just too much unreliability in the signal. So the hope is to do something to build a project there. And so here are schematics of what you might do. Well, let me begin with the Earth, of course. The SKA, its low frequency version, should be under construction in the next few years with maybe 100,000 antenna. These are simple tripoles. So this demonstrates that one can work at low frequencies, but it's on the Earth, unfortunately. This would be in the Australian desert, radio quiet, but maybe not quite radio quiet or not quite ionosphere free enough to the ultimate signal. So the idea is that on the moon, one has far better conditions. This is a schematic, an old idea for just to give you a feeling for one could do. You would want an interferometer. You'll be laying down, these are printed strips of dipoles, correlated somehow by either microwaves or coaxial cables to synthesize a signal. You want to look at a wavelength of roughly 10 meters, right, 21 centimeters. And so that's good in a way. It means you need very simple, dipoles. The odd rock or two doesn't matter on the surface. You could have, meter boulders all over the place that wouldn't make much of a difference. You want to be looking at rather high resolution, ideally wave numbers of 10 inverse megaparsecs. That's corresponds to wave numbers, 100 times better than you can actually do easily with the CMB, or 10 times finer resolution, which means you're opening up many thousands, it goes as the cube of K, of course, many thousands more modes, which is why you can do so well. The optimal array would have to be maybe 100 kilometers across to accommodate all of these modes. And you'll need millions of dipoles to give you the sensitivity you need. But again, these numbers are not so different from telescopes we're planning already. It's a scaled up version. It's known technology, it's doing it on the moon, that's all. Here is the real problem though, that at these low frequencies, you have a really bright foreground in the sky from galaxies, from all the usual things that give you low frequency radio emission. And you're looking for a 10 millikelvin. If you remember my previous figure, that was roughly the signal you're looking for, the shadow of these clouds. So that you need to beat down this noise by of order 100,000 or something. So can you do that at all? Well, there are schemes. So here is one of the more adventurous parts of the project. You want to sort out all the radio sources in the sky. So the idea is to build a huge single dish telescope on the far side of the moon. So it's Arecibo style, right? Or fast style, I should say, to be current. That's the Chinese analog of Arecibo. And that is filling a big crater with some deployable wire mesh and having a suspended receiver, and then being on the far side because you have this amazing radio quiet properties, and you do source surveys and help sort out the foregrounds. So that would be a crucial part of this future project. You need an interferometer over large patches of the far side, plus a dish like this to do a combined experiment in the future. Okay, so what sort of cosmology could you do with this? Well, here is what I think the goal is. You could actually, in principle, search for and have a good chance of detecting primordial non-Gaussianity. So it's going to be tough, as I've said, finding signals of dark energy or dark matter, and no guarantee with the CMB. But if I talk about generic inflation, then thanks to the work of many people, Matarese most recently, the FNL prediction, the deviation from Gaussianity is of order 1%. So express that in terms of the temperature fluctuations. So it's a high order perturbation of the temperature fluctuations. In general, you have nonlinear corrections, you have quadratic effects coming in the inflation modeling, and this gives you intrinsically non-Gaussian features because of multiple fields, for example, and other effects like that. And so you're looking for a tiny correction. Why is it so small? Well, it turns out that the generic expression is something like the scalar index, the power of the fluctuations, minus 1, and that's of order 0.01. So you're looking for tiny corrections, 1% to the quadratic of the temperature. And that is hugely, hugely difficult. And so how on earth do you get to such amazingly tiny numbers? Well, it's all a question of counting bits of information. And the idea goes something like this, that our current limits with the CMB are something like FNL is of order 10, upper limit. And we have 1 million bits of information. When we go to galaxy surveys, we'll have roughly 100 times more bits of information. And the prediction is, from the modeling of the surveys, we should be able to improve FNL by a factor of 10. But it's only by really beefing up our information content, and that, I'm afraid, means the far side of the moon and nothing else, that we can pick up our trillions of modes and avoid all of this ionospheric mess, that we could have a hope of getting down to 0.01. And that would be the holy grail for a prediction of inflation. So there you have it. That's basically the main cosmology message. But I'm not going to stop there, because let me emphasize that the moon is something for the young people in this audience, right? Those of us who are actively teaching now, I mean, I'm obviously long out of this game, but we're talking about 30, 40 years from now to build these magnificent projects. And so that means, our graduate students being the prime of their careers when these things come to fruition. And they can do cosmology, they can tackle the future of cosmology, but let me show you the most amazing things in addition to low frequency radio astronomy. So the idea is that we can put telescopes on the moon in dark polar craters. And so they're wonderful places. They're very cold, and they're permanently shadowed. It's a great place in principle to do astronomy, and you could build bigger telescopes than you can on the Earth. And as I'll explain in a second, it's size of the telescope that counts. So here's one example of where you might put such a telescope. It's in the Shackleton crater near the South Pole. It's dark all the time because it has high rims. The sun never, really gets above those rims, in the daytime. It's near the pole. It's cold, and from the rims, which are so high, they're always in sunlight. So you have a source of solar power very close by. And then it turns out that these craters are full of ice. It seems there are various ways, I would explain how these are done, But we've recently, over the past few years, measured traces of ice, and that's wonderful for doing construction and doing all sorts of other things, making rocket fuel things on the moon. In fact, it's one of the main motivations for going to the moon, to help develop the moon, that we have sources of ice available for us. There'll be a competition with astronomy, but hopefully we'll be piggybacking on these other projects to do this. Okay, so then let's suppose now that we're in our dark crater and we build a telescope. Well, my first comment is that we can build a really, really big telescope. So here's a telescope that never saw the light of day on the Earth. It was called OWL, the Overwhelmingly Large Telescope concept. Never saw the light of day, it was just too big. It would have fallen over under Earth's gravity, or the winds would have blown it down, or whatever. But on the moon, we have low gravity, we have no winds, the stresses are moderate, etc. On big structures. We could build 100-meter class telescopes. If we do that, then here is, I'm going to mention one or two amazing things one could do with these telescopes. So one is to measure the first stars. So you need, redshift 20 or so. You need something like a fraction of a parsec resolution. Here's a simulation. So this will be an image that you could get of an H2 of the first stars at redshift 20 or thereabouts. That's one example of the science you could do with such a big telescope. But there's another thing you could do, which I find, actually really incredible. And this is something that you will have to agree with me does overlap with cosmology. And that's the following. It's looking for exoplanets. So in our future of exoplanet exploration, it's all about looking for biomarkers, evidence for life, etc., one form or another. And the key thing underlying all our future searches is yield. We need a large number of targets to study, which are rocky exoplanets in not too far from their parent stars, typically G stars or solar types, or maybe M stars. And LUVOIR, our current best bet for the future for studying exoplanets, will have of order, if we're lucky, 50 targets, Earth twin-like targets. But if we can go to build a 100-meter class telescope, then the horizon opens up dramatically. We suddenly are looking at tens of thousands of targets. And there's no reason really to stop at 100 meters. One could build bigger things too eventually. And so we suddenly will get so many target exoplanets that only with large numbers will there be some possibility, of success in finding our signatures of maybe not so simple forms of life. So that's one great reason for building big telescopes on the moon. Okay, so that's amazing, but there's even one more step I want to take you to. It doesn't end there. So here maybe is the most dramatic thing in optical astronomy that I've ever seen. And so this is a futuristic plan. Again, let's go to a crater is the idea. And you put lots of mirror segments. These are 5-meter mirrors on tripods with focal camera in the focal plane, strung out from cables around the surface. And the idea is that you can use interferometry to coherently synthesize the images from these telescopes. So in principle, you can build a 5-kilometer aperture telescope, right? A hyperscope, it's been called. And it would have a resolution of tens of micro-arc seconds. And so this is something that one could in principle do on the moon. And with this sort of resolution, which is thousands of times more than we would be getting from a 100-meter class telescope, you could do the equivalent of imaging the nearest planetary systems. This would be the equivalent of imaging the planets around, Proxima Centauri, for example. We don't need to send gram-sized micro cameras on Project Starshot to look at these things for a fraction of a second. We could actually build a telescope that would image our nearest exoplanets and look for oceans and mountains and lakes and seasonal variations, incredible things. Maybe the glows of cities at night, that sort of thing. You know, if they're inhabited, which of course is highly unlikely, but one never knows. So that's the exoplanet imaging story, which is not directly cosmology, but of course, if we can discover that we're not alone in the universe, it would certainly be a gateway to cosmology that we couldn't even begin to dream of. Okay, so let me then conclude with one or two more cosmology-directed applications on the moon. So my next example is going to be in far infrared astronomy. And so one of our greatest goals there is to look for spectral distortions in the microwave background. So we have this wonderful black body spectrum from the Fire-Scobie experiment. No deviations are seen to pass in 100,000. And an important prediction of the lambda CDM model, our standard cosmology model, is that in addition to the microwave background giving you all galaxies and so forth, which we see in the fluctuations, we see in large-scale structure, etc., the seeds from which these formed, all that can be mapped. On very small scales, there is a host of structures whose baryons have long since dissipated by friction, but leave distortions as they do so in the microwave background. And this we should see, it's a guaranteed signal, a guaranteed test of the model by looking for deviations in this. And so there is a project called EL3, the Large Logistic Lander of ESA, to launch a 1.5 ton cargo to the moon in the next 5 years or so. And let's imagine one could put an experiment on board to measure spectral distortion. So what would this experiment look like? Well, this is a brief summary. It would be a Fourier transform interferometer. It would have two inputs. One that's much like, the Scobie-Forrest experiment, but it would have two inputs. It would look at the sky and look at a reference black body and look for differences, looking for distortions. And so you'd need to put this in a container that cooled things down to a couple of degrees, 2.5 degrees Kelvin. You need a reasonable sized telescope, but 1.5 meters is nothing much. You're looking at the terahertz range. You could put several modules inside this EL3 payload. It wouldn't need to point at the sky. It would just sit there. And as the sky moved, rotated, the moon rotated around the Earth, you would see different parts of the sky. And that would be enough to scan the sky. And you could, in principle, improve over Fire-as by 5 orders of magnitude. And that would open up this new terrain. So what is this new terrain that you could do in far infrared astronomy? Well, this shows you the intensity versus the frequency of the distortion. So here is where Fire-as was back in 1990. And the amazing thing is we have done no better since then. And so we proposed experiments. This is one called Pixie to look for improved signals, but that has not been funded. And this new idea of doing something on the moon would take us down basically to this level somewhere around here. And you can see what opens up when you can do this is not just the signals that come from the so-called relativist gas distortions, the Y distortions, that's the red and the blue lines. Let me not talk about those. But we're now looking for this signal from early galaxy formation. Mu is the chemical potential. That's a significant distortion of the microwave background. And this is the positive part. It's suppressed. This is in quadrature. This is the signal you're getting. And you should easily be able to resolve these distortions. But maybe the most amazing thing of all that you could do is you'll be looking at the early universe as it recombined when you look at the microwave background spectrum. And in principle, when it recombined way back at redshift 1000, you see a recombination spectrum. You have hydrogen, you have helium atoms, and they recombined. And they should have spectral lines. And here you see their spectral lines. So wouldn't it be amazing to look for spectral lines from the Big Bang? This would be the most amazing test, I think, of standard physics applying way back, 300,000 years after the beginning. Um, Spectral lines are the bread and butter of astronomy. We could be doing that in cosmology too. Okay, so I have one more example for you of what we're going to be doing on the moon. So just to finish here, we would be testing cold dark matter. We'd be looking for recombination lines way back to redshifts of 10,000. What I didn't mention was that if there were anything strange going on in the universe, such as black holes decaying or dark matter decaying or annihilating, we could be seeing exotic inputs very easily in these distortions. But that's more speculation. That's not a guaranteed return. So my final example is going to be this. The biggest revolution in our field in the past decade has been the discovery of gravity waves from merging black holes. So we have, 3 ground-based detectors now in operation, more soon coming online. It's a growing field. But all of our ground-based detectors look in a certain frequency range, and they, span the Earth. And so they give you, by triangulation, they can give you a position, but the position is pretty ambiguous. It's 20, 30 degrees accuracy. If you were to go to the moon actually is an excellent receiver for gravity waves. Remember the early days we had gravitational bar detectors? They were very, very sensitive, but they didn't have a very broad frequency response. That was the early ideas about looking for gravity waves, and we've since moved on to the interferometric techniques. But the moon actually is a wonderful bar detector. Why? Because the moon, unlike the Earth, is very stable seismologically. It doesn't have any moving tectonic plates. It doesn't, have earthquakes, moonquakes. Now and then an asteroid, hits. Now and then tidal effects give you slight displacements of the moon's core. So you get signals, but all of those you can monitor. And so if you were to stick a few seismometers on the lunar surface, only 3 or 4 actually, you'll get an amazing way of looking for gravity wave signals. And the beauty of this is that now, we're exploring the gravity wave landscape. I mentioned our terrestrial detectors, LISA, Virgo, etc., which explore this frequency range. This is the Hertz frequency range. LISA in space will take us to millihertz. We also have pulsar timing array. But now we can in principle devise something on the moon. We can suddenly do 2 things. One is with triangulation with the Earth, we can pinpoint where those sources are coming from because we overlap in frequency with the Earth. And then secondly, we can bridge the gap between LISA and LIGO. LISA is the low frequency. You see the merging black holes spiral in together, and you can watch that evolution with our gravity wave telescope on the moon. So amazing science awaits us by doing gravity wave astronomy on the moon. Okay, so I've given you a tour of all the many things one could do on the moon, many in cosmology, some way beyond cosmology. So let me now try to tell you finally why I think none of this is crazy. This is all on our horizon, actually. So the reason is that various space agencies, and it's not just NASA, it's China especially, also Russia, even India and Japan, are all planning explorations of the moon. The 2 major space agencies are talking about a lunar space station and manned exploration, but the others will do that eventually too. And the idea is to have infrastructure in place within about 10 years from now. And this idea of a lunar village, there already are design plans out there by, I've seen them by European architects, for example, working for ESA. And it's driven by a lot of interest to exploit the moon. First of all, I mentioned there's a lot of ice on the moon. it will be a great place to make rocket fuel, liquid hydrogen, liquid oxygen, which would be ideal for traveling back to Earth and in the solar system. So that's it's the future of space travel, interplanetary travel, certainly. On the moon, there's extensive commercial interest in mining. It turns out that on the Earth, we're running out of rare earth elements, things like europium and so forth, critical for computers and cell phones. Semiconductor materials, we're having crises. The moon is absolutely loaded with a supply of these rare elements, vital elements, strategic elements that are, thousands of times more abundant than on the Earth, millions of times actually. All of that thanks to bombardment by asteroids over billions of years that have left a rich legacy on the moon. And then finally, I would say maybe the biggest driver of all, which is why one of the main reasons we'll go to the moon, inevitably, I think, is commercial interest in tourism. It's considered to be, the new frontier. Right now, it's for a wealthier segment of our society. It will cost you 50 million plus to get a ticket for a trip around the moon, or probably far more actually. But eventually the prices will come down, and I think you have to think 20, 30 years ahead, and it's all going to change. And my point is really, let's build telescopes. It's such a tiny fraction of the total cost. Now, you may say that this is a long, long way away. Well, it's true, but nothing has stopped my particle physics colleagues from planning 100 TV collider for roughly the year 2050. This takes at least 20 years of design, 20 years of construction, probably far more. And so we're discussing very similar timescales for our lunar projects. The cosmology, I've tried to argue, is unparalleled. I don't think you can do it on the Earth. I don't think it's realistic to imagine these mega projects I've described being done in space. The budget will just be horrendous, but because we're going to the moon anyway, it seems to me it's a reasonable thing to spend a few percent of our resources on. That's all it will take to do these mega telescopes. And we do have this past analogy for the Hubble telescope. I really don't think would have really done that if it were not for the fact that it was just a small part of a much larger space exploration exercise. Okay, so that's really what I want to tell you about. So astronomy's future is on the moon, and here is a very brief pastiche of all you can see about the projects from, recently announced by Europe and Russia and China, and even our latest administration in the US is going forward with this. So I think, to summarize, there really is space for telescopes out there on the moon. Thank you.
Thank you, Joe, for this fantastic perspective that brings us to 2050. So really, thank you so much. So I'm sure there will be many questions and curiosities. So if anyone wants to ask a question to Joe, you can write it on the chat or switch on your mic.
Can I speak? This is Reno Malaysi speaking. Hello, Joe.
Hello.
Can you hear me?
Yes, I can.
Okay, fascinating talk. I agree that there is space for telescopes on the moon, and but as you probably certainly know, what will drive astronomy on the moon will be something which has nothing to do with astrophysics. I mean, there will be other interests, and at the end, if the technology would be acquired, at that point, astronomy will be feasible on the moon. Let me make as an example the Hubble Space Telescope, which probably you know came out almost free of charge, since the technology was developed by NASA and other agencies at that point for looking down, for looking at the Earth. So at the end, when they decided that the technology could be used, even looking on the sky, the Hubble Space Telescope was almost free of charge. And this will be, according to what I can understand, this will happen also on the moon. There will be other interests up to the point at which the governments or the various countries will use some of the money for astronomy. I don't know if you agree.
Yeah, I entirely agree with you. You know, the Hubble Space Telescope still was expensive. My estimate is that it still costs, you know, a few percent of the total budget that was out there for the space station and the shuttle. But really, the technology was not the issue, as you say, that had been solved. But I think we only had those telescopes because we already had the space shuttle in place, the infrastructure in place to deliver them into orbit. So that made such a big difference. So I'm optimistic that there'll be a similar story for the moon. We'll be laying down all sorts of probably robotic exploration issues on the moon, and one obvious training task for much of what we do there might well be to find sites for telescopes and build telescopes. It's such simple technology in principle, at least if you start with the radio telescopes. And even now, as we develop our ideas for landers on the moon, we're looking for payloads. And I think the payload selection will include, possible astrophysics experiments, which will be, telescopes, maybe pilot telescopes are the ones I've talked about. But that certainly is very much on the near-term horizon, the next 5 years.
Thank you, Joe. So I don't see any other questions on the chat, but I'm sure there might be some others. So I encourage people to switch on their mic eventually. Alfredo Luminari, please go ahead.
Hi, I'm Alfredo Luminari from Rome, and I would like to thank first for the very interesting talk. And my question is a very general one. I would like to know if, together with not just telescope, but all the space, the lunar exploration project, all these projects came also with some idea of the environmental impact, or both for the moon and for the space, or these are just explorative ideas with not yet a firm evaluation of the consequences? Because all these projects are really start to build hugely for what concerns moon. So I think it would be also time to see which will be the impact on our fellow satellite.
Yeah, that's a real concern. I think one is very worried about pollution on the moon. So all we have so far is the Outer Space Treaty from 1967. So far, I think 110 countries have signed up to it, the United Nations. So that is something that at least does, have good words about avoiding pollution, and it's concerned about having rights, property rights. So it discourages that. It discourages any military activity on the moon, that sort of thing. But it's clear that there's no enforcement involved, and there are many questions that are unanswered, and besides which things have moved on so much since in the recent decades. I think we desperately need a reinvigorated legal framework for future activities on the moon, as the different countries, China, Russia, US, Europe, etc., all are competing to land in a restricted number of sites, maybe, and also perhaps to do their own exploitation activities on the moon. You know, who has first rights to whatever. These sort of things has to be decided in some congenial way without conflicts. So I think we have time now to develop these these ideas, these regulations. But so far, it's pretty much you know, an open book. Unfortunately, the rules have yet to be written.
Thank you, Joe. So there is Elia Battistelli.
Hello. Thank you very much for the very nice talk. Thanks a lot. So I have a question about spectral distortions. You mentioned about the possibility to make a measurement of spectral distortions from the moon, which, as you said, is something that we really need. I mean, it's a long time. I mean, our limits are still the one from fire, so 30 years ago. So my question is, it would be really great to have these kind of constraints from a telescope from the moon. I don't know if you have ever done a comparison about a telescope on a moon and a telescope, for instance, on L2. And of course, I'm referring to ground pickup, which for monopole measurements can be an important issue for this kind of measurement.
Yeah, so that's an interesting point. I've not looked at that specifically, but let me just say that when the size of such a telescope that's needed was estimated, it was as a free flyer, it was going to be really, really expensive. I think if you look in the Voyager 250, the ESA exercise to look at futuristic projects, they do have such an experiment. Is one of several, as well as a lunar version. So it's certainly being considered, but I think the pros and cons I've not seen evaluated though of the issues like pickup.
Thank you, Joe.
Thank you very much. Thanks a lot.
So if there are no further questions, I would take the chance to ask one. So you have brought us to 2015, until 2050. And in the meantime, we are very close to another revolution, that is the James Webb and Euclid. So what do you think of the near future? What do you think that, how do these future, coming missions will change our perspective even towards the very far future?
So I think it's all part of the grand scheme of things. JWST, Rubin, etc. They're going to improve our understanding of cosmology. Our parameter estimations will increase in accuracy by factors of a few, that's for certain. But I'm not entirely sure that they're going to fundamentally probe the beginning of the universe. That's why I think we have to keep an open mind on looking for, the grander scale, the longer time scale, the more ambitious experiments that go beyond these. So they're just limited in scope, inevitably, just because the number of galaxies is limited. That was my argument, really. You can do just so much. It'd be wonderful if they do, for example, detect new physics in cosmology. I think it's an open question. They might well do. There are certainly many inflation models which predict signals that would be unique and interesting, that are, within the possibilities for large-scale surveys of the future. But there's no guarantee. But something fascinating could be up there. So I'm optimistic, but I think we should very much keep the door open on what happens next.
Sure, we will then. Okay, so if there are no further questions, I would really want to thank again Joe for this beautiful and inspiring talk, and I hope really to meet you soon in Rome next year. So you remember that you have this open invitation. And so thank you again. So I would ask the attendants to leave the room, and so that the PhD students can freely interact with you and ask questions they have. Okay. So thank you again, Joe, and I really hope to see you soon.
Me too. Me too.
I still remember, Joe, when I met you in Strasbourg, in one of a PhD school in Strasbourg. It was 1996. And you asked me, what are you going to work on? Because I was starting my PhD, and I answered, well, I think galaxy evolution. And you said, that's a perfect choice because we are never going to solve that. So you will have, many things to do, and it's true.
True.
So goodbye, and I
Okay.
really hope to meet you soon in Rome. Thank you.
Bye, Raffaella. Thank you. Thank you.
Thank you. Goodbye.